So elemental analysis, etc. With elemental analysis, you don't figure out how much sulfate, you figure out how much sulfur, how much oxygen, using different techniques. Lots of different techniques out there. For example, analyzing moon rocks, what they took up is an XPS. It's an X-ray photoelectron spectrometer in which they blast the rocks or minerals with X-rays and knock core electrons off. When they knock core electrons off, the valence electrons fall down and emit light, certain frequencies of light. And those frequencies of light are characteristic of the particular element, so they can analyze this element by element depending on what frequencies of light are emitted from the sample. And so we do elemental analysis. From elemental analysis, typically what you get is a not a typical formula, because a formula is an atom or mass, atom or mole composition. Usually from elemental analysis, we get a percent by mass composition. And so they'll say, oh, you have X grams of magnesium. And then you know the total mass, so X grams of magnesium divided by the total mass times 100% gives you the percent magnesium by mass in the sample. And so we can go element by element and see how many grams of each element were determined or found in that particular sample. And so here, let's say I had a 100-gram sample. Say I had a 100-gram sample, and 11 grams of this was hydrogen. 11 point something, close to 12 grams hydrogen. So that's around 12% hydrogen. Then, it can be costly, so hopefully you have an idea of what elements to expect. So, when I sent out samples, it was about $200, it's probably more now, $200 per element to analyze how much is in there, since we didn't have the equipment ourselves. And there's lots of labs specializing in this. In fact, the samples I sent out to Gardena. There's a lab here in Gardena that does this. And then I just have a checklist, analyze for this element, this element, this element. I don't want to analyze for the whole periodic table. That would be too expensive. But I had an idea what was in there. And so next element I'll analyze for is oxygen. It was about 88% oxygen. And so this sample was about 12% hydrogen, 88% oxygen. What is it? What is it? It's water, right? Water is H11O88, or around there, H12O88. Did you know that? You probably didn't know that because we aren't used to looking at compositions based on percent by masses. If you were to represent water in terms of percent by mass, and I need my calculator. My calculator's on my phone. That's what we'd have. But, it's inconvenient to represent compositions by percent by mass because, all these percent by masses is like, 11.88 whatever. I don't know how many digits you're going to get out there. They aren't nice whole numbers, right, by mass. But if we do it by atoms, then it becomes nice whole number ratios, according to the law of multiple proportions. So what we do is we convert the percent by mass composition into a formula over here. A formula is a mole or atom ratio. And so the typical steps is you assume 100 grams. And then if we're given a percent by mass composition from our analysis, we assume 100 grams, and then we convert everything into moles, right? And then find the simplest mole ratio. And so we get grams to moles, and then figure out the mole ratio, whatever mole ratios. And that would give us our atom ratio, moles of atoms. So I assume everyone's done this, right? Going from percent by mass composition to chemical formula. Well, there are other techniques here, and so let's focus on some of the other techniques. One of the techniques that's used for organic, because organic most organics are electron rich, they're flammable, right? And so a lot of organics, we can just burn them. And so we burn them. One of the techniques that we have available is something called combustion analysis, which is inexpensive. And anybody could set this up with inexpensive lab equipment. It's not that difficult. For carbon, hydrogen, and oxygen, it's not that difficult. For other elements, it becomes a little bit more difficult, but still doable. All right, so let's take a look at combustion analysis of organics. This combustion analysis works on anything that you can burn, basically, and then capture the products. And so this one, you know, the starting point for these type of calculations is just percent by mass composition to the formula, or we can go from the formula and go backwards to percent by mass composition. Okay, like I said, I'm skipping that, but going straight to combustion analysis. But you have some homework problems with percent by mass composition, and you can go back to Chem 4 and look at those. There's a lot of those problems. So combustion analysis, we just burn the sample. And the sample, you know, it's organic. So organics contain carbon, what? Carbon and hydrogen for sure. And then the next most common would be carbon, hydrogen, oxygen, sulfur, phosphorus, nitrogen, etc. What we're going to look at is we're going to look at carbon, hydrogen compounds, you know, CH. We got CH compound, and we burn it. This is a hydrocarbon. We burn it in excess O2. Then we're going to form CO2 and H2O. And so we can track this. You know, all the carbon that was in our original unknown, you know, here, CX, all this is going to end up here. You know, it's X, CO2. And then all the hydrogen that was in there, the Y, will end up over here, you know, in the H2. Y over 2 of H2O. And so using some stoichiometry, we can figure out, you know, how much hydrogen, you know, we have, because what we can do is we can trap the water in a desiccant. And so you weigh the desiccant before, you weigh the desiccant after, and the desiccant absorbs all the water, so it's going to get heavier. And so we can get the grams of water. From the grams of water, we can get the moles of water. Moles of water, we get the moles of hydrogen. Moles of hydrogen give us this. And then over here, the CO2 we can trap using like a hydroxide.
Is that Y over 2 or Y over 2?
Y over 2, sorry. Over here, we could trap the CO2 in some chemical agent that likes CO2 and then weigh it before and weigh it after, conservation of mass. Right? And then figure out the grams of CO2, the moles of CO2 to moles of carbon, and we get the ratio. You know, we figure out the simplest whole number ratio between the moles of carbon and the moles of hydrogen. And so you probably did something like this in Chem 4. And then it gets a little bit more complicated when you have a CHO. If you have a CHO, you know, then we have to do an extra step to figure out oxygen. Because if we're doing CHO, the complication comes when we burn this, because we burn this in excess O2. And so we lose track of the oxygen. And we can't track it because what we're going to get is we're going to get CO2 and water. And so the carbon here is no problem. Carbon, we could track the CO2. The hydrogen is no problem. Track to H2O. The oxygen gets mixed up. And so this is what we have to do. We do an extra step here. And so the extra step is we go from grams of CO2 to moles of CO2, moles of CO2 to moles of carbon, moles of carbon, we have to go all the way to grams of carbon. We don't stop at moles of carbon and get the ratio. We go back to grams of carbon. And then from grams of H2O, we go to moles of H2O. From moles of H2O, we go to moles of hydrogen. From moles of hydrogen, we're going to go to grams of hydrogen. And so to get the grams of O2, the grams of O2 is equal to the total grams, let's say grams of CHO, minus the grams of C minus the grams of H. That gives us the grams of O2. And so from the grams of O2, what we'll do is we'll go to moles of O2. So we stop here. And then what we'll do is we'll go back to moles. Go back to moles of C, and then go back to moles of H, and then just get the simplest mole ratio. Moles of carbon, moles of hydrogen, moles of O2. That'll give us a chemical formula. For other things like CHS, we could do it in the same way. You know, burn it in excess O2, and we get CO2 plus H2O plus typically SO2 or SO3, etc. And so method one, we do the difference, you know. Method two is we just go grams of SO2 to moles of SO2, etc., or SO3. Depends on how much you oxidize it, you know, what you use to trap it or analyze it. And so method one is the difference. So it would be grams of CHS minus grams of C minus grams of H gives us grams of S. And when we get grams of S, we could go to moles of S and figure it out. You know, just like we did with oxygen. So here, etc. CHN. CHN, there's some additional CHN compounds, which typically are called amines, or they could be, if there's an O, it could be nitro. But you burn these in O2, and then you get CO2 plus H2O plus NOx, you know, oxides of nitrogen. It's usually a mixture. X, you know, is variable. And so it depends on the combustion conditions. You could form N2O, dinitrogen monoxide, or nitrous oxide. You could form nitric oxide, or NO, nitrogen monoxide, or NO2, nitrogen dioxide. These are called NOx, or NOx. We lose track of the nitrogen there, and so we are. And so what you do is you analyze a separate sample. So this one you can figure out the carbon, the hydrogen. On the next one, we figure out, like, we take a CHN and further process it, undergoing numerous steps to N2. And then you can figure out nitrogen. Here, this is analyzing for nitrogen. And so from the N2, you can get moles of N2 to moles of N. Figure it out. This one is a little bit complicated because we're doing two separate reactions. And so two analyses. But we didn't have to. We could use method one and do it by difference. But sometimes we have CHNO. If we had CHNO, then yeah, you know what, we're going to have to do, you know, two different analyses because we can't do it by the difference. And so we would do, we'd get carbon and hydrogen and then analyze for nitrogen and oxygen some way. Probably analyze for the nitrogen and figure out the oxygen by difference. Does that make sense? And so these are some examples of combustion analysis here. Where am I supposed to be at now? What does the syllabus say?
Chapter 4 right now.
Chapter 4 right now? Okay. Well, Chapter 3, you know, if you have some problems with that, let me know. We can work out the problems. I'm going to skip the homework problem for Chapter 3 and move on to Chapter 4. Yeah. Chapter 4 deals with chemical reactions. Basically, Chapter 4 is stoichiometry. So we're going to have this regular stoichiometry here, limiting reactant. Just remember limiting reagent problems, limiting reactant problems. And so just standard stoichiometry. That's what we should get from Chapter 4. So let's take a quick overview of Chapter 4. Chemical reactions. You know, these are the observations you usually take. You know, precipitate, what's the color of the precipitate? What's the form of the precipitate? You know, is there gas involved? Is there heat? Etc. So just observations that we typically take. This type of reaction, we have different kinds of reactions. This one's called a metathesis type reaction. Here, it's precipitate. This one is a redox reaction. This is a penny and nitric acid. This is another redox reaction. This is combustion of something here. Burning. Wire gauze, steel wool in air. And so we'll look at different types of reactions. We have to balance the reactions. I think balancing equations should be pretty basic, so I'm skipping that. Let me know if I need to cover it. Sometimes we use more specific details for reactions, like this delta just means what? Heat. But sometimes we need the temperature because the slight changes in temperature will result in different products being formed. And so this is kind of an interesting reaction here. This one happens at 350 degrees C, 340 atmospheres, in the presence of these two things are catalysts, zinc oxide and what is this called? Cr2O3. Cr2O3. Well, is it ionic or molecular? Ionic. What's the chromium on? Is that variable charge or fixed charge? Variable. So this is chromium 3 oxide here, and so the presence of that. But this reaction is kind of interesting. Carbon monoxide plus hydrogen yields methanol. And so here we're making an organic from two inorganics. Carbon monoxide is typically a lot of it is an inorganic, hydrogen is inorganic. And so we can make an organic chemical methanol using that. It's a redox reaction. Here's another example of a redox reaction. Burning hydrogen and oxygen to form water. It was a violent one. All right, so what we're going to have is we're going to have our stoichiometry map. And so let's take a look at stoichiometry in Chapter 4. You know, stoichiometry, if you recall, we need a balanced chemical equation to go from moles of A to moles of B. And so that's why they spend so much time talking about balancing chemical equations, because we need the mole ratio. Right? The mole ratio, we're either going to get from the balanced chemical equation or from the formulas. Formulas are already mole ratios, right? And so normally in Chem 1A, you know, the simplest would be just going from grams of A, you know, the mass of A to moles of A, grams of A to moles. And then we go to moles of B, and then to grams of B. So that's your basic stoichiometry problem. But in Chem 1A, we're going to do things a little bit more complicated than Chem 4. So in Chem 4, though, you dealt with mixtures too. In Chem 1A, we're going to deal with mixtures. And so we might have, instead of this, we might have grams of mixture. If we have grams of mixture, we can figure out in this mixture how many grams of puree is there if we have the percent composition by mass. And so if we have 100 grams of mixture and 20 grams of that 100 is A, that's 20% A, then we can figure out 100 grams of mixture is only going to give us 20 grams of A. And so typically we deal with this type of mixture here. We can deal with other types of mixtures as well. Solution mixtures, you know, these are, let's talk about that here. Let's fast forward. Well, actually, let's just take a look at this one here. Here, this one requires some additional steps because they give you a volume of a mixture. You know, they have an alloy here consisting of aluminum and copper. And so they give you the volume of the alloy. And so from the volume of the alloy, which is the mixture, we had to go to grams of mixture using the density of the mixture. So they give us the density of the mixture. And then from the grams of mixture, we can go to grams of pure aluminum by using the percent by mass composition, which they give us here, 93.7%. And then once we're there, then we just have the standard problem here. So this one involved a couple of additional steps here, which we see here. Let's take a look at another one here. This one is a liquid mixture, but again, this is by mass. This is 28% HCl by mass, 28.0%. What volume of this solution is required to completely react with 1.87 grams of aluminum in the reaction? And so they give us 1.87 grams of aluminum. So we can go from grams of aluminum to moles of aluminum. And then we need the equation, the balanced chemical equation, which is given somewhere, to go from moles of HCl, oops, what are we doing? Moles of aluminum to moles of HCl in the balanced chemical equation. Moles of HCl to grams of HCl. This is grams of pure HCl. And then from grams of pure HCl to grams of HCl solution, which is done by the percent by mass composition, and then grams of solution to milliliters of solution if we know the density. The density of this is 1.14. So we could do that. And so some variations to our stoichiometry map shown here. You know, but the most common way of expressing mixtures in aqueous form is not percent by mass. You know, for HCl it is. For concentrated HCl, 28%, 36%. You know, but we usually use molarity. And so molarity is expressing the mixture composition in terms of moles of solute per liter solution. So we're given the volume of the solution in liters, and we can figure out how many moles of solute we have. And so that takes us directly here. You know, if we have the volume of solution, A, and then the molarity, and we can figure out how many moles direct. Okay, so that's that. Now this is something you're going to have to do in class, so this is kind of a side topic here, and that is solution dilution. You know, solution dilution is you take a more concentrated solution and make a more dilute solution. Have you used the equation M1V1 is equal to M2V2 for solution dilution? I think everybody has in Chem 4. Well, this is just an illustration. So we take a concentrated chromate solution, and so you measure out a volume of concentrated, and then you dilute it. This is called a volumetric flask. And what we do is we carefully dilute it up to the line. There's a calibration line here, and this delivers 250.00 milliliters. It's designed to contain. And so we just add water until we hit the 250 and then shake. Actually, we try to shake it before we fill it, because once you fill it up to here, it's hard to agitate the solution. And so this is called solution dilution. You have some problems with solution dilution here, which is illustrated here. Just concentrated and then adding water to get the final. This is a MIBI, MFBI type problem. Okay, another solution dilution. Here they're showing the pipetting. You're going to have to do this pretty soon, actually. And so you want to use a pipette, either volumetric or more. Pipette, the concentrated, dilute to the mark. The calculation is fairly straightforward. Okay. All right, then we have limiting reactant problems. You know, which one is a limiting reactant? There are two methods for doing limiting reactant. One is the comparison of moles method, which you might have or might not have talked about in Chem 4. I skip it. I do the smaller amount method. Which reactant produces the smaller amount of product? That's the one. The smaller amount of product is called the theoretical yield. Right? And sometimes we don't get that because you lose stuff. And so we have a percent yield. Percent yield just compares the actual yield with the theoretical yield. Theoretical yield is determined from the limiting reactant. This is more of after you've done it, after you've done the synthesis, after you've done the reaction, how much did you actually get and how much did you lose? Okay. So, sometimes this loss is very important because the losses can occur in sequence. And so what happens is, let's say you lose 5%. Let's go to let's say you lose 5% in reaction, so you got a 95% yield. But then you take the products from the first reaction and then subject those to a second reaction. And then you lose some here, 5% yield, say, or 95% yield. And then you take the products from here and then use them in the next step. And so you have a sequence of steps, a sequence of reactions. And so the percent yield is very important because what happens is after a long sequence of reactions, you might be left with barely any product at all. You know, and this is often the case. You do like a series of 10 reactions, and by the end of that, you barely have anything left. Sometimes you have nothing left. This happens in Chem 1B when people are trying to, and also in Chem 4, you guys had qualitative analysis where you did a sequence of reactions. You know, and sometimes people lose a little bit in each step, and by the end they have nothing there. The test negative for a particular ion. And so we have to worry about that in consecutive reactions. And so we're going to look at consecutive reactions here later. And so this is all pretty much review, I think, the stoichiometry. And so we'll just do some problems just to refresh our memory how to do these stoichiometry problems. All right, let's take a look at number 26 here. This one, I chose this one because it's not so easy to balance, maybe. Or maybe it is. You know, sometimes you just get lucky and balance this quite easily. But anyway, we're taking aluminum and the other, what's that other thing called? Tell me what that is, the name of it. Anybody? Okay, then you definitely have to go back and do your flashcards or whatever. Aluminum plus, what's the name of this? Ammonium perchlorate. Okay, you're good. But if that wasn't at the tip of your tongue, then you need to do some review. Ammonium perchlorate, solid. Ammonium salts are soluble, so there must be no water around to make this solid. And so aluminum plus ammonium perchlorate, what do you think is going to happen? And so you look at this reaction. Does this look like a double replacement reaction to you? Does it look like a single replacement reaction to you? Maybe. You know, single replacements have the form A plus BX, right? And so this is actually a single replacement. But you look at the products. Doesn't that look like the products of a single replacement reaction? No. And so unfortunately, this, even though it's set up like a single replacement, this is not, you know, not a single replacement actually. This is an example of a redox reaction. And redox reaction, we're looking at electron rich and electron poor. And so which one is electron rich, the aluminum or the ammonium perchlorate? Electron rich. What's the oxidation state of aluminum? Zero. Is that electron rich or electron poor or just neutral? It's actually electron rich for aluminum. All metals are electron rich. One of the properties of metals is they tend to lose electrons. Why do they tend to lose electrons? Because they're considered electron rich. They tend to lose electrons when undergoing chemical reactions. Ammonium perchlorate consists of two ions. It consists of ammonium ion. Ammonium ions, are those electron rich or electron poor? Well, the way we figured this out is by looking at the oxidation states. So what are the oxidation states in ammonium? Which goes first, hydrogen or nitrogen? I'm not going to write the Lewis structure for this, but you could. Hydrogen or nitrogen? Hydrogen at +1. +4, that means nitrogen must be -3 to add up, right? Is it electron rich or electron poor? It's electron, well, if you look at the hydrogen, it looks like it's electron poor, but hydrogen in a +1 is not that unusual because water has hydrogen in +1 state. It's not that reactive. But nitrogen is electron rich. And so ammonium is electron rich. So we have two electron rich species. We have aluminum and ammonium. There must be an electron poor species, and that must be perchlorate. Perchlorate. Perchlorate is, what is that? Electron rich or electron poor? Well, first you look at the oxidation states. You know, a lot of people say electron rich because it's a negative. It's got an extra electron, right? An extra electron, it's got to be electron rich. And, you know, paradoxically, you know, this should be poor because it's got a positive charge. A missing electron. The missing electron certainly must be poor, right? No, because this is the net charge. You know, when we do oxidation states, we don't look at the net charge. We look at the charge on each individual atom. Sometimes the net charge is the same as the charge on the individual atom for monatomics. It always is. But here, we look at the charge. What goes first, chlorine or oxygen? Oxygen. You know, usually the more electronegative element goes first because that's going to get its charge that it wants because it's more electronegative. And then chlorine. What's the charge on chlorine? Minus 2 times 4 is minus 8. Minus 8 plus 7. Is plus 7 a happy charge on chlorine? Well, let's take a look at the periodic table. What do you think? Looking at the periodic table, plus 7 implies that chlorine just did what? Plus 7 on chlorine, a plus 7 charge on chlorine means chlorine just lost all its valence electrons. Do you think chlorine's going to be happy losing all 7 of its valence electrons? No. And so perchlorate is what we call dangerous stuff, you know? It's dangerous stuff because we say it's extremely electron poor, meaning it's a powerful, we call it powerful oxidizer. Powerful oxidizer. And so, in fact, ammonium perchlorate is a very dangerous chemical. Why is ammonium perchlorate a very dangerous chemical, even without the aluminum here? If there's no aluminum here, I'd be very, very worried about ammonium perchlorate because, why? You know, the same thing happens here. In this room, is the air in this room stable? Yeah, but what if I fill this room up with methane? Now, is the air in this room stable filled with methane gas? No, because now I have, you know, if I have oxidizer like O2 alone, no big deal because there's no fuel around, right? Well, there is, but it's not, I'm not going to have to worry about spontaneous combustion. But if I have this room filled with methane, well, now I got a really good fuel because methane is very electron rich, right? -4 on that carbon, which means I got a fuel and oxidizer mix. In other words, I have what we call a reducing agent and an oxidizing agent, a strong reducing agent and a strong oxidizing agent mixed together. Is that a good idea? No, it's not a good idea because it's going to be unstable. It just needs a spark, right? Well, ammonium perchlorate's the same thing. Ammonium perchlorate all it needs is a spark. Why? Because ammonium perchlorate is a compound, this is a solid compound that is a mix of a powerful reducer, ammonium, and a powerful oxidizer, perchlorate. And so, in other words, ammonium perchlorate is what we call an explosive because it could potentially detonate because you got ammonium, the fuel, and the oxidizer in the same compound. What's preventing this from reacting? Well, it's in the solid state, so hopefully the ions stay in position. But what happens if you heat this stuff up? The ions start to vibrate and will potentially do what? Do this. Let's see. There's a huge one. There's a big explosion in Nevada, I think. Or was this a fire? It could be fire or it could be explosion, depends on how fast. Ooh.
That's gonna be loud.
Do you think ammonium perchlorate is a happy chemical? No, no, it's very unhappy. This happened recently. This isn't that long ago. There's an enormous explosion in Nevada. But anyway, yeah, this is very dangerous because you got the fuel and the oxidizer in the same compound. There's another one, right? There's another one that that happened. What do you think about this? This is ammonium perchlorate. This is called Ammonium nitrate. Is that a happy compound? No, this is like filling up the room with hydrogen. You know, if I sat here and filled up the room with hydrogen gas, would you be happy? You'd probably be pretty unhappy, right? Because all it would take is a spark and then have a huge fire or explosion. Well, the same thing here. Why is this unhappy? Because I know ammonium is electron rich or electron poor. Well, it's got a positive charge, so what does that mean? Poor or rich? No, you can't tell from the net charge. You got to look at the individual charges on the atoms. So we saw that -3 + 1. This is electron rich. How about nitrate? -2. Nitrogen is +5. With nitrogen in +5, apparently nitrogen must have done what? If nitrogen's +5, then nitrogen must have lost all of its valence electrons. If nitrogen's in -3, then that means it's got a full octet of electrons. So one nitrogen has a full octet of electrons, the other nitrogens lost everything. Do you think those nitrogens are happy being next to each other? What's going to happen if nitrogen got into a tug-of-war with nitrogen? A nitrogen-nitrogen tug-of-war. Which one's going to win? You know? And so anyway, well, it depends on what's bonded to it too. You know, this one happens to have oxygens. But nonetheless, you know, is this a happy situation? What do you think? And so what do we call this? The fuel is called the reducer or the oxidizer? The reducer. So we got a powerful reducer with a powerful oxidizer. What do you think? What do you think? Redox reactions are different than, you know, precipitation. You know, these double replacement reactions. You know, these double replacement reactions, you don't get this kind of energy released. You know, we'll talk about why when we get to the energetics of this. But this was a massive. I mean, it's hard to see the scale, but this is far away. I mean, this is a massive explosion. Probably better videos of this, but. Oh, Texas is.
Do it yourself or something.
Yeah.
Redoing it.
I don't want to.
I
Yeah.
bet our labor gets down to help you find the perfect innovative appliances to help.
Let's I'll give you one of the more famous. You know what the deadliest industrial accident in the U.S. was? Let me just make sure I'm sure this is still the deadliest industrial accident in the U.S. Deadliest industrial accident. I know Bhopal was awful, but Bhopal was something else. I need to get part 1. Part 3, shoot. I mean, where's part 1? It would happen in 1947. I don't want too long of a one. Let's see. Are you okay with graphic images? Let's see. There's a number of them, but just forgot to bring the link. I wasn't planning on showing this today, but I'll go ahead and show this.
air and the way. Yeah.
You can't spend much time in Texas City with all the big ships that come and go, the oil and chemical refineries, the pipelines and storage tanks brimming with flammable products. You can't spend much time here without thinking the unthinkable. Could it happen again? Could Texas City be another boom town in the worst possible way? Years ago, Texas City burned its way into the nation's conscience. The worst industrial accident in American history made Texas City synonymous with disaster. The day it happened, Will Lane was very near the epicenter.
It was real strange. I'm real glad to be alive.
Lane was a young chemist at the Monsanto chemical plant. He remembers seeing the bright orange smoke from a burning ship. Firefighters were busy pouring water on the French freighter Grand Camp at the city docks across from the Monsanto plant.
You could look at it and real pretty to watch. And there were townspeople by the hundreds that lined the part of our parking lot that was nearest to the ship. They came down to watch a fire.
Texas City had a new fire truck, and this was its first day out. 27 firemen were on the docks trying to put out the fire. The burning ship was so hot, the water around it was boiling. But as a chemist, there was something about that orange-colored smoke that worried Will Lane.
We could just see bits and pieces of paper bagging going up to the air and away. And my boss thought, and I thought too, that we were witnessing a nitrate fire. But someone had said, it's a grain ship, and the grain was on fire.
So believing it was only a matter of time before the fire was out, Will Lane went back to work at the Monsanto lab. But the fire was growing hotter, and the orange smoke was attracting an even larger crowd along the docks.
It was a very, very strong sulfur in the air, sulfur fumes.
Herb Metzger watched the fire while talking to a group of high school kids.
This smoke was just a beautiful orange.
Right, it was.
Mary Hunter, a Monsanto secretary, was watching from her office window.
And across town, Mrs. Knappenberger, a housewife with a home camera, came here to the Texas City dike to get a closer look at the burning ship. She didn't know it then, but she was about to record America's greatest man-made disaster.
The ship had been loaded not with grain, but with ammonium nitrate fertilizer, the same ingredient that would be used years later in the Oklahoma City bombing. The Texas City blast was so strong it registered as an earthquake in Denver, 900 miles away. It created a tidal wave that washed a barge into a parking lot. 2 airplanes circling the ship were blasted from the sky. Flying debris punctured chemical storage tanks, creating an even larger inferno.
We have another truck up here off of the road. It had about 10 or 15 men, and they were all crushed.
The explosion killed at least 581 people, including school children who had come to watch the fire. But the danger was far from over. Tomorrow, we'll hear the stories of survival and courage from the people who were there 50 years ago. Charles Hadlock, 11 News, Texas City. Tomorrow, we'll hear the stories of survival and courage from the people who were there 50 years ago. Charles Hadlock. This is Charles Hadlock. Texas City has tried to outlive its past, but it's hard. There are so many reminders. An anchor here, a propeller there, and sad, sometimes painful memories all around.
Even today, 50 years later, the tragedy is not forgotten. 6th Street, the once busy main street of Texas City, has been renamed the Street of Memories. For it was along this street that so many screamed and ran for their lives.
The explosion of the French freighter Grand Camp left an entire town dazed and confused.
And I ran as fast, as hard as I could.
There are many stories of survival. Dr. Will Lane was in the Monsanto lab. He had been watching with suspicion the bright orange smoke of the burning ship docked next to the plant when it suddenly exploded.
lights just went out. I could not see more than 2 or 3 feet. And I thought, my God, it was a nitrate explosion. I thought I'd lie right here and be burned to death.
He got up, looked over his shoulder at the burning tanks of benzene, and ran for his life.
Passed a car in which 2 people have been decapitated. Then I passed one of the 2 little planes that had been flying around overhead, came down along the path that I took up into town.
I'm sure all of that glass came into us, and I must have gone like this. And so my arm was injured all in here.
Mary Hunter was also in the Monsanto plant. To this day, she still has shards of glass in her body.
I had it cut out of me, but luckily it had lead in it. And therefore when they x-rayed it, they could find the glass.
Before the explosion, hundreds of people were on the docks, including Herb Metzger.
I had turned to walk away. I had my back to the explosion, but the force hit me in the back, and it sort of just, I don't know, I would say it picked me up, but it moved me forward 20 or 30 feet.
Suddenly, pieces of the ship were falling all around him. He crawled under a car.
A couple of pieces hit the car. I could feel it, you know, when it jarred, but nothing hit me.
Here comes another explosion.
But pieces of metal did hit the High Flyer, a second ship loaded with ammonium nitrate. Efforts to tow the burning ship out to sea failed, and 14 hours later, it exploded. The fires burned for days. Nearly 600 people died, and 5,000 were left injured or homeless. Those who survived helped each other.
We had to pry some folks out that had telephone poles, in fact, I guess, or some kind of big poles going across them. They obviously were crushed, you know. It was not a nice sight, but kind of steeled myself to it for a while.
Even after the dead were buried, many survivors never talked about it again. But over the half-century since the explosion, they rebuilt their lives and their city. That must have been a hard thing to do, with so many memories around. Charles Hadlock, 11 News, Texas City.
Okay, so, you know, just by simple full chart, no, these aren't full charts, these are what? Simply looking at the oxidation states of these compounds can tell you a lot about the chemistry here, what's going on. And so obviously this is bad as well, ammonium nitrate solid. You know, at room temperature it's probably okay, just like here. You know, as long as this is at room temperature, methane and oxygen, I'm not going to expect to explode, you know, but you elevate the temperature or you introduce a spark, then we're in trouble, right? And so that's what we call metastable. Metastable mixture is, it's stable until something knocks it and causes it to react. Well, this, you know, this aluminum, what do you think is a better reducer? You know, aluminum or ammonium? Well, apparently aluminum must be a pretty good reducer, or, you know, they're just fueling this with extra fuel. You know, when I look at this, I see fuel, aluminum and ammonium, and I see oxidizer or chlorate. For predicting reactions like this can be complicated. Actually, fortunately, I have to bring that up again. And so the products you would see are for redox are a little bit complicated, even though this kind of looks like a single replacement type form that is A plus BX. It's actually not so easy. The same thing goes with combustion. You know, when you're doing combustion of a hydrocarbon, you know, under what conditions are you going to generate carbon monoxide? And so, like, if I'm burning methane here, am I generating any carbon monoxide, you think? You know, what if I cut down the air intake, and I get a yellow flame? Am I generating some carbon monoxide? Yeah, I mean, I'm not getting complete combustion. I am going to generate some carbon monoxide. Now, how much am I going to generate, and under what exact conditions will I generate that? Do you want to use theory to predict that? You know, a lot of people want to use theory to predict it, but sometimes it's very difficult to predict, you know, exactly what you're going to get in particular chemical reactions. And so what's often done in this is just to go ahead and do the reaction and then see, oops, wrong chapter, see what products you form. And then change the conditions, and then determine integrated. What number was that? 76? 26? See what forms. And so here, you know, what forms is, okay, we oxidize aluminum completely to aluminum oxide, Al2O3 solid. This will be complete because aluminum is now in the 3+. We also oxidize it to AlCl3, then we form some H2O and nitrogen. Under other conditions, we might get NOx. You know, we need very high temperatures and high pressures to get NOx. So it depends on, and actually we need lots of oxygen. We don't have that much oxygen here. And so under these conditions, we get this. Now, would this have been easy to predict, these products? No. And so that's what's often done in redox reactions. You mix it together and you see what happens. So this is the case here. We mix this together, see what happens. Well, we're going to get a lot of energy. This is rocket fuel, basically, solid rocket fuel. Now, here, let's go ahead and balance this. And so how do we want to balance this? Well, when we balance complicated reactions like this, the easiest thing is to save single elements for last. So we'd save the aluminum for last and the nitrogen. You know, single elements are easiest to balance at the end. And then we try to balance the more complicated things first. And so one thing would be, let's see, which should we balance first?
Chlorine.
The chlorine?
Yes.
All right. If we balance the chlorine first, we see we have 3 chlorines here. We have 1 chlorine here, so we could just balance it by doing a 3 there. Okay, now we fix this. So we don't want to touch this, and we don't want to touch that, right? We fix that. Okay, then, well, if this is fixed, then we have, what, 3 nitrogens here. If we got 3 nitrogens here, we have 2 nitrogens here, so how can we get 3? How we can get 3 is we're just going to use a fraction. We're going to multiply by 3 halves. The 2 cancels, leaves us with 3 nitrogens. And so now we got 3 nitrogens, 3 nitrogens. We don't want to touch this now because it's balanced, right? And then just go down the list. How many hydrogens we have? 12 hydrogens. Only place for hydrogens is here, so that's going to give me 6 here. So that's 12 hydrogens. Okay, that's going to give us 6 oxygens. 6 oxygens plus 3 gives us 9 oxygens. Over here I have 3 times 4 is 12 oxygens, so I don't have enough oxygens here. And so the only way to boost the number of oxygens would be to go from 3 to 6. So I got 6 oxygens plus 6 oxygens, which would give me 12 oxygens, and then just balance the aluminum. So that gives me altogether 4 plus 1 is 5 aluminum, so we get 5 aluminums here. And so this strategy, sometimes it's just luck, balance, it works out or it doesn't work out. All right, what is the minimum mass of ammonium perchlorate consumed per kilogram of aluminum? And so minimum mass of ammonium perchlorate per kilogram. So we have 1 kilogram of aluminum. So we go from 1 kilogram of aluminum to grams of aluminum, 1,000 grams per kilogram. And,
aren't you supposed to multiply everything by 2, since that's a fraction instead of nitrogen?
You could, yeah. We could multiply by 2. Sometimes we leave it as fractions. We don't always get rid of the fractions. But in stoichiometry, it's probably easier to do a whole number. So you could just go 10, 6, 4, 2, 12, 3 as the mole ratios. All right, so we go from kilograms to grams of aluminum to moles of aluminum to moles of ammonium perchlorate using the mole ratio, a 10 to 6 or 5 to 3 mole ratio. From moles to grams of ammonium perchlorate to kilograms of ammonium perchlorate. What we're going to do is we're going to use 2 decimal places for the molar masses. That should give us enough, except for hydrogen. When we do hydrogen, we don't use 2 decimal places. With 2 decimal places, that would give us 3 sig figs. Usually we want 4 sig figs. And so what we'll do for hydrogen is we'll use 1.008 alone. But if we use hydrogen in another compound, then we'll use 1.01. So ammonium perchlorate's quick because, when you do it to 2 decimal places, you can figure things out quite quickly because you use them so much, you memorize them. So nitrogen's 1401. We have 4 hydrogens. Each hydrogen's 101, so we get 404. A chlorine is 35.45. An oxygen, we have 4 oxygens. Each oxygen is 1600, so that's 6400. And so molar masses become a lot quicker to calculate, when we just do it to 2 decimal places. If we use H alone, then we're using 1008, or H2. If we do H2, it's going to be 2016. So we get 4 sig figs. Otherwise, we're going to have 4 sig figs here. Does that make sense? For the molar masses. And so this is just your straight stoichiometry style problem here. Yeah. So we go kilograms to aluminum to grams of aluminum. Okay. We'll stop here, and then we'll look at some more stoichiometry.